I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on the center of mass for individual objects and systems of objects. So in this video, we're going to talk about center of mass for individual objects and systems of objects. So the center of mass is a point at which all of the mass of an object or system is considered to be concentrated. So when considering the center of mass, we have to consider the mass distribution. And the first thing we want to do is we're going to use symmetry to figure out where the center of mass is, a point, a line, or a plane to figure out the center of mass. Then we're going to break the object into parts to find the center of mass of each part, and then choose our axes wisely to find, and we'll go through an example to see what that looks like. So for solid objects, the center of mass, we're just going to pick the geometric center of the object. So here's a box. The geometric center of the box is the middle. That's the center of mass. Like the cars that we've been using, we've used the mass as 0.25 kilograms, but that's really, we're using the center of mass of that moving car as it's rolling across the ramp. If we look at the center of mass of a circular object, so that's like a tire rolling, the tire, the symbol, the center of mass is going to be the center of that object. If we look at this donut shape, we can see that the place where there is the center of mass, there is no mass. So it's possible that the center of mass of an object may not have a mass at that point at all, or specifically a collection of objects. So let's take a look at an example for center of mass for collection of a 4 kilogram mass, a 5 kilogram mass, and a 7 kilogram mass oriented in this way. So the 4 and 5 kilogram mass, let's say that they're 30 centimeters apart, and that the horizontal distance between the 5 and 7 is 20 centimeters, and the vertical distance between the 5 and 7 is 10 centimeters apart. So instead of leaving these as lines, let's make this into an x and y coordinate system. So we're making it into a plane, an x and y coordinate system, where the coordinate of the 4 kilogram is 0, 30, the 5 kilograms at the origin, and the coordinate of the 7 kilogram is 20, 10. So we're going to calculate the system center of mass by using these two equations, one for the x coordinate of the center of mass and one for the y coordinate of the center of mass. So we're going to add up individual masses in coordinates and divide by the total mass. If it's three-dimensional, then we'd also use the same equation for the z coordinate. But in intro-level physics course, we're going to keep it simple and just keep it as 2 dimensions. So the xcm and ycm represent the coordinates of the center of the system mass. So the x coordinate and y coordinate. Mi is the individual mass values. Xi and Yi are the individual mass coordinates in terms of the way we defined our XY plane, and we can define it any way we want, but it's easiest to put one of the masses at 0, 0. And then capital M is the total mass of the system, so 7 plus 4 plus 5, which would be 16 kilograms. So let's go ahead and find the x coordinate of the center of mass. So what we're going to do is we're going to multiply each mass by their individual x coordinate, 5 being at the origin, 0, 4 also being on the y-axis of 0, so the 7 kilogram is the only one that has a coordinate of 20 centimeters. Then we're going to take that value and we're going to divide it by the total mass, 4 plus 5 plus 7, so our total mass is 16, so 7 times 20 gives us 140 centimeter kilogram, divided by 16 kilograms, which gives us an x coordinate of 8.75 centimeters, which is approximately this location here. Doing the same for the y center of mass coordinate, we take the individual masses. The 5 kilograms still has a y coordinate of 0 because it's at the origin, and the 7 and 4 kilogram both have coordinates, 7 being 10 and the 4 being 30. We divide by the total mass, we get 190 over 16, which is 11.875 centimeters, which is approximately right here. So now we have the x coordinate, which is here, and the y coordinate, which is here. So we look at that as an ordered pair, and we've now located the center of mass of these three objects oriented in this fashion. So that's how you calculate the center of mass of each individual object. What if objects are moving and we want to find the velocity of the center of mass? So the way we're going to find the velocity of the center of mass for a singular object, that just means it's whatever the translational velocity is, like we've done with the cars. So if we have a box that is moving across the table, the velocity of the center of mass is going to be the translational velocity of that block as it slides across the table. Now, what if we have a system of objects? So the velocity of the center of mass is dependent on two things, the total mass and the system momentum. So if we have two objects that are moving, we'd add up the individual momentum, taking into account direction, and then we'd add up the masses and we would divide those to find the velocity of the center of mass. So looking at an example problem, two objects moving at the same speed of 1 meter per second. One has a mass of 2, the smaller one has a mass of 1. We want to find the velocity of the center of mass before the two blocks collide. So as the blocks move towards each other, before they collide, we want to find the velocity of the center of mass. So we know that to find the velocity of the center of mass, we can find the sum of the individual momentum and divide that by the total mass. Well, to find the sum of the total individual momentum, we know there's going to be a collision occurring, so we could draw a momentum bar chart. And you can reference the video that's linked above for drawing momentum bar charts. The smaller box moves in the positive direction, the larger box in the negative direction. So that means the larger box moving at the same speed is going to have more momentum. So we multiply their mass times velocity. We get 1 kilogram meter per second for the smaller and negative 2 kilogram meter per second for the larger box. So summing those up, 1 plus negative 2, and then we divide by the total mass of 3, and we simplify. We get negative 1 kilogram meter per second over 3 kilograms. The units simplify to meters per second, which is a velocity. We get negative 1/3 meter per second. So we have found the velocity of the center of mass before the collision, but what's the velocity of the center of mass of the two blocks after they collide and move to the left? Well, now we're just going to use that same momentum bar chart and finish it and look at the final situation. So we know that if we have negative 2 plus 1, that's going to give us a total momentum of negative 1 kilogram meter per second. Well, during a collision, the total momentum is conserved. Therefore, the momentum of the system is still the same. So that means the velocity of the center of mass is the same. So we can use that same equation to prove this, that the velocity of the center of mass is going to equal the sum of the total momentum, which is negative 1 kilogram meter per second, divided by 3 is going to give us that negative 0.33 meters per second. So that means the velocity of the center of mass depends on the total momentum of the system, and momentum is conserved in all collisions. That means that the collision within a system does not change the velocity of the center of mass. So if two objects are moving and we're sketching a velocity time graph for those two objects, that means if they collide, if we're sketching the velocity time graph for the center of mass, there is no change in the velocity of center of mass when the two objects collide. This is an intro to center of mass and how to calculate it and velocity of center of mass. I hope this was helpful, and I hope you have a great day and an even better tomorrow.
If you found this video helpful, click the like button down below and subscribe to my channel, Happy Coaches, and follow me on Instagram and Twitter at Happy Coaches.